Dear students, as we have already discussed the concept of Z transform, in this video we will solve some additional problems on Z transform. First problem, find the Z transform of a power n into e to the power minus a divided by n factorial. Since Z transform is linear, so that Z transform of a power n into e to the power minus a divided by n factorial can be written as e to the power minus a into Z transform of a power n by n factorial. Here, e to the power minus a is independent of n and it will act as a constant term so that you can take it out from the Z transform. Now, how you can find Z transform of a power n by n factorial? We know the damping rule. According to the damping rule, if you know Z transform of un is u of z, then Z transform of a power n into un can be obtained by replacing u of z by a. Therefore, e to the power minus a into Z transform of a power n by n factorial becomes e to the power minus a into Z transform of 1 by n factorial and replace z by a. Referring from the previous video, Z transform of 1 by n factorial is e to the power 1 by z. Therefore, e to the power minus a into Z transform of 1 by n factorial will be equal to e to the power minus a into e to the power 1 by z, but just replace z by a. After replacing z by a, you will get Z transform of a power n into e to the power minus a divided by n factorial as e to the power minus a into e to the power a by z. On simplification, Z transform of a power n into e to the power minus a divided by n factorial becomes e to the power a into 1 minus z divided by z. Now we'll prove a result. Z transform of n power p is minus z into d by dz of Z transform of n power p minus 1, where p is a positive integer. Let us consider the right hand side of the equation and try to obtain left hand side. That is minus z into d by dz of Z transform of n power p minus 1. From the definition of the Z transform of n power p minus 1 can be written as summation n from 0 to infinity n to the power p minus 1 into z to the power minus n. Taking the differential operator inside the summation so that differentiation of z to the power minus n is equal to minus n into z to the power minus n minus 1. Multiplying z to the power minus n minus 1 so that the power of z changes to minus n, that is summation n from 0 to infinity n to the power p into z to the power minus n, which is nothing but Z transform of n power p, which is equal to the left hand side of the equation. Hence the proof. Next problem, that is to find Z transform of cos of n pi by 2 plus pi by 4. As you cannot evaluate directly, so using the expansion of cos of a plus b, Z transform of cos of n pi by 2 plus pi by 4 becomes Z transform of cos of n pi by 2 into cos of pi by 4 minus sin of n pi by 2 into sin of pi by 4. By using the linear property of Z transform, the above equation becomes cos of pi by 4 into Z transform of cos of n pi by 2 minus sin of pi by 4 into Z transform of sin of n pi by 2. But we know that Z transform of cos n theta is Z into Z minus cos theta divided by Z square minus 2Z cos theta plus 1, and Z transform of sin n theta is Z into sin theta divided by Z square minus 2Z cos theta plus 1. By using it, you'll get Z transform of cos of n pi by 2 plus pi by 4 as cos pi by 4 into Z minus cos pi by 2 divided by Z square minus 2Z cos pi by 2 plus 1 minus sin pi by 4 into Z sin pi by 2 divided by Z square minus 2Z cos pi by 2 plus 1. But cos pi by 4 and sin pi by 4 is 1 by root 2, and cos pi by 2 value is 0 and sin pi by 2 value is 1. By substituting and on simplification, you will get Z transform of cos of n pi by 2 plus pi by 4 as 1 by root 2 into Z square minus Z divided by Z square plus 1. In the same way, let us evaluate Z transform of cos of n pi by 8 plus theta. By using cos of a plus b, Z transform of cos of n pi by 8 plus theta can be written as Z transform of cos of n pi by 8 into cos theta minus sin of n pi by 8 into sin theta. By using the linear property, the above equation reduces to cos theta into Z transform of cos of n pi by 8 minus sin theta into Z transform of sin of n pi by 8. But Z transform of cos n theta is Z into Z minus cos theta divided by Z square minus 2Z cos theta plus 1, and Z transform of sin n theta is Z sin theta divided by Z square minus 2Z cos theta plus 1. By using it and simplifying, the equation reduces to Z into cos theta into Z minus cos pi by 8 minus Z into sin theta into sin pi by 8 divided by Z square minus 2Z cos pi by 8 plus 1. Next problem. Find Z transform of cos 3 theta. Since cos 3 theta is independent of n, which will act as a constant term, therefore Z transform of cos 3 theta can be written as cos 3 theta into Z transform of 1. But Z transform of 1 is Z divided by Z minus 1. Therefore, Z transform of cos 3 theta is Z into cos 3 theta divided by Z minus 1. Next one. Evaluate Z transform of 2n plus sin n pi by 4 plus 1. By using the linear property of Z transform, you can write Z transform of 2n plus 5 into sin of n pi by 4 plus 1 as 2 times Z transform of n plus 5 times Z transform of sin of n pi by 4 plus Z transform of 1. But Z transform of n is z by z minus 1 whole square. The transform of sin n theta is z into sin theta divided by z square minus 2z cos theta plus 1, and the transform of 1 is z divided by z minus 1. By using this result, the transform of 2n plus 5 into sin of n pi by 4 plus 1 becomes 2z divided by z minus 1 whole square plus 5z into sin pi by 4 divided by z square minus 2z cos pi by 4 plus 1 plus z divided by z minus 1. Next problem. Find the z transform of cos theta plus I sin theta whole raised to n. We know that cos theta plus I sin theta is e power I theta. So cos theta plus I sin theta whole raised to n becomes e power I theta whole raised to n, or k power n, where k is e power I theta. But the transform of k power n is z divided by z minus k. Therefore, the transform of e power I theta whole raised to n is z divided by z minus e power I theta, or the transform of cos theta plus I sin theta whole raised to n is z divided by z minus e power I theta. Next problem. Find the transform of cos hyperbolic n pi by 2 plus theta. By the definition of cos hyperbolic theta, the transform of cos hyperbolic n pi by 2 plus theta can be written as the transform of e power n pi by 2 plus theta plus e power minus of n pi by 2 plus theta divided by 2, or can also be written as the transform of half times e power theta into e power n pi by 2 plus e power minus theta into e power minus n pi by 2. By using the linear property of z transform, the above equation becomes half times e power theta into z transform of e power n pi by 2 plus e power minus theta into z transform of e power minus of n pi by 2. But z transform of e power n pi by 2 is z divided by z minus e power pi by 2, and z transform of e power minus n pi by 2 is z divided by z minus e power minus pi by 2. By substituting and on simplification, you will get z transform of cos hyperbolic n pi by 2 plus theta as z by 2 into z into e power theta plus e power minus theta minus e power pi by 2 minus theta plus e power minus of pi by 2 minus theta divided by z square minus z into e power pi by 2 plus e power minus pi by 2 plus 1. But e power theta plus e power minus theta can be written as 2 times cos hyperbolic theta. Therefore, the transform of cos hyperbolic n pi by 2 plus theta becomes z square into cos hyperbolic theta minus z into cos hyperbolic pi by 2 minus theta divided by z square minus 2z cos hyperbolic pi by 2 plus 1. Next problem is on initial value theorem. If u of z is equal to 2z square plus 5z plus 14 divided by z minus 1 whole to the power 4, Find u2 and u3. To get u2 and u3, first find u0 and u1. By the initial value theorem, u0 is limit of u of z as z tends to infinity. By substituting u of z, u0 becomes limit z tends to infinity 2z square plus 5z plus 14 divided by z minus 1 whole to the power 4. Since the degree of the numerator is less than the degree of the denominator, therefore u0 is 0. u1 is limit of z into u of z minus z into u0 as z tends to infinity. Substitute u of z and u0. You will get u1 as limit z tends to infinity 2z cube plus 5z square plus 14z divided by z minus 1 whole to the power 4. Note that degree of the numerator is less than the degree of the denominator. Therefore, u1 is 0. Now, u2 is equal to limit of z square into u of z minus z square into u0 minus z into u1 as z tends to infinity. By substituting u of z, u0 and u1, u2 becomes limit z tends to infinity 2z to the power 4 plus 5z cube plus 14z square divided by z minus 1 whole to the power 4. Take z to the power 4 outside from the numerator as well as the denominator so that you can cancel the term which is giving trouble to apply the limit. After applying the limit, the value of u2 becomes 2. The last term is u3 and is equal to limit of z cube into u of z minus z cube into u0 minus z square into u1 minus z into u2 as z tends to infinity. By substituting u of z, u0, u1 and u2, you will get u3 as limit z tends to infinity 2z to the power 5 plus 5z to the power 4 plus 14z cube divided by z minus 1 whole to the power 4 minus 2z. You can't directly apply the limit. Further simplification is needed. By taking the LCM and by simplification, you will get u3 as limit z tends to infinity 13z to the power 4 plus 8z cube plus 4z square minus 2z divided by z minus 1 whole to the power 4. By taking z to the power 4 outside from the numerator and denominator and by applying the limit, you will get u3 equal to 13. Last problem. If u of z is equal to 2z square plus 3z plus 4 divided by z minus 3 whole cube, find u2 and u3. u0 is limit u of z as z tends to infinity and which is equal to 0. u1 is limit of z into u of z minus z into u0 as z tends to infinity. By substituting u of z and u0, u1 becomes limit z tends to infinity 2z cube plus 3z square plus 4z divided by z minus 3 whole cube. Since the degree of the numerator and the degree of the denominator are equal, therefore, by taking z cube outside from the numerator as well as the denominator and by applying the limit, the value of u1 becomes 2. Similarly, u3 is limit of z square into u of z minus z square into u0 minus z into u1 as z tends to infinity. By substituting u of z, u0 and u1, u2 becomes limit z tends to infinity 2z to the power 4 plus 3z cube plus 4z square minus 2z to the power 4 plus 18z cube minus 36z to the power 2 plus 54z divided by z minus 3 whole cube. Cancel 2z to the power 4 and minus 2z to the power 4. Take z cube outside and then apply the limit so that you will get u2 equal to 21. u3 is equal to limit of z cube into u of z minus z cube into u0 minus z square into u1 minus z into u2. By substituting u of z, u0, u1 and u2 and on simplification we will get u3 as limit z tends to infinity 2z to the power 5 plus 3z to the power 4 plus 4z cube minus 2z to the power 5 minus 3z to the power 4 plus 135z cube minus 432z square plus 567z divided by z minus 3 whole cube. Cancel 2z to the power 5 and 3z to the power 4. After cancelling, numerator and denominator both are degree 3 polynomials and hence the limit is the coefficient of z cube. In the numerator it is 139 and in the denominator it is 1 and hence u3 is equal to 139.